Okay, so everybody has come back. You can hear me, right?
Yes, ma'am.
Okay. Okay, so let us start. Okay. So now you have known about the grid chamber. So what is the work for the grid chamber? It is used to remove the grids, okay, like sands, debris, all those things it removes. So now we will proceed to one numerical. But before doing the numerical, uh, just wait. Let me see. Okay, oh no, one more thing is there. Okay, so grid channels, they are of your two types. Okay, so here you can see this one horizontal flow type, and one is your aerated flow type. Okay, so what it's written here, you see, in the horizontal flow type, the flow passes through the channel in a horizontal direction. Okay, the chamber, it is designed to give a horizontal straight line flow velocity which is kept constant over the varying discharge. Okay, so the horizontal flow, it gives you the flow, it passes through a horizontal direction. Okay, it's a simple. And one is your aerated type of grid channel. Okay, so the aerated type of grid channel, it consists of a what, a spiral flow aeration tank. Okay, and where the spiral velocity, it is controlled by the shape of the chamber and the quantity of the air supplied to the unit. So in the aerated type of grid channel chamber, your air is supplied, okay, to with the help of air. Your these things are like these grids, sands or debris, those are removed. So one is your horizontal flow type of a grid chamber, and the other one is your aerated type of grid chamber. And the aerated type of grid chamber, it consists of spiral flow aeration tank. Okay, so now next is your this constant velocity horizontal flow grid chambers. Okay, so here it is nothing much to discuss, but there are certain formulas you can see, like here this formula, critical scour velocity. Okay, this formula, like for the horizontal velocity formula, you need to use this. So like next is your, okay, so let's start. Let's do one numerical. Then I think we will be knowing the what are the values that we should remember. Okay, so this is a numerical. You see the question. It is written here. A rectangular grid chamber is designed to remove particles with a diameter of zero point 0.2 millimeter. So the particle size has a diameter of zero point 0.2 millimeter, and it has a specific gravity of 2.65. Okay, so settling velocity for these particles has been found to range from 0.016 to 0.022 meter per second, depending on their shape factor. A flow through velocity of zero point 0.3 meter per second will be maintained by proportioning where determine the channel dimensions for a maximum wastewater flow of 10,000 cubic meter per day. So what are the things that are given here is that your dimensions of your particle size is given here, diameter and specific gravity is mentioned, also the settling velocity of the particle, it has been mentioned. Okay, and your the quantity of wastewater, what is the quantity of wastewater, that is given. So here now the horizontal velocity, it is here given as your zero point 0.3 uh, 0.3 meter per second. Okay, here your flow velocity, it is given as your zero point 0.3. Here you see this one. Okay, it is given as your zero point 0.3 meter per second. Settling velocity, it is also it is given, the range is given. Okay, so it is between 0.016 to 0.0 0.22 meter per second, but you need to choose any one value between these two, because we have to proceed using that one value. So here in the book they have considered it to be 0.020. Okay, so they have considered this 0.020. So you can assume it to be 0.018 also, 0.019 also, doesn't matter. Okay, since it is a design problem. So in between this range you can choose any one value. So they have choose it to be 0.020. Okay, so now we need to find out the area. Okay, we need to find the area, and we know the formula for uh, any formula to find out the area is equal to q is equal to av. Okay, q is equal to av. So here v is your horizontal velocity, because we have the in the question it is mentioned that the flow is moving horizontally and the velocity is 0.3. So vh, you have to write the v as vh, okay, into a. So a we need to find out. So have the q value also. Okay, q it is given that the the quantity of wastewater is your 10,000 cubic meter per day. Okay, in the question it is mentioned here. So this 10,000 cubic meter per day, they have converted it to meter cube per second. Okay, so you have to convert it to meter cube per second by dividing by 24 into 60 by 60 into 60. Okay, then you will get it in meter cube per second. Then you have the value for v, you have the value for q, then you put it in the formula and you will get the area value as your 0.385 meter square. Clear? So next step after finding the area, they have assumed something. Okay, so since it is a design problem, your some values it might not be given in the question, so you have to assume something by yourself, or actually in the these theories of this grid chambers, there is written all these things. Okay, so here now you need to note it down. This one is that you have to assume if the water depth is not given. Okay, if the water depth is not given, you will assume it to be like 1 meter. Okay, you assume the water depth to be 1 meter. Okay, and the water depth it is kept to be like 0.3 meter above the channel bottom. Okay, so here it is you need to find out the width. Okay, for finding the width we have this formula, depth into width is equal to what? 0.385 is the area just now we got. So area L into B or H into B. Okay, so here we are finding the width. So 1 meter they have taken the depth, so your width will be same 0.385, or you can say they are taking it as a whole number, or you can say it is 0.4 meter. Okay, so now you need to find out the overall depth of the grid chamber. So like we have designed for your tank. Okay, for your raw water, what I have told you that is that when you design a tank, so you have to consider the overall depth. Okay, so when you consider the overall depth, a freeboard, the freeboard will come. Okay, so what is freeboard I have already discussed in your first module, so I won't be repeating. So your overall depth while you find out, so you have to add the with the water depth, you have to add the freeboard. Okay, so here they are taking the freeboard as your 0.45 meter. Okay, and they are adding it with your like the water depth. Okay, so now they are adding all these things and they are getting it to be 1.75 meter, the overall depth. Okay, so now they are finding the settling velocity. Okay, since here we are designing the tank and we need the length, breadth and width. Okay, so here now after you have got the width. Okay, you have got the depth, now you need what? You need the length. So you have to find the length. So how to find the length is that the velocity, settling velocity, it is 0.020. Okay, like from the range we have selected one velocity. So now we need to find out the detention time. So the detention time formula is this one. Already also you got in while doing the raw water sedimentation tank formula. Okay, so here also this is the formula for your detention time. So it is water depth, we have assumed it to be 1, and settling velocity is 0.02. So you got it to be, the detention time is what, 50 seconds. Okay, so now you need find out the length of the tank. So what is the formula for length of the tank? It is VH, that is your velocity in the horizontal direction, into your detention period or detention time. So VH, how much you got? You got it to be 0.3 into 50 meter, or it is your 15 meter. Okay, so length of the tank, you got it to be 15 meter. So now again you see here, you read this line, the length of the channel is increased beyond theoretical value by a factor of 10 to 50% to account for non-idealities in the flow and settling of the particles. Okay, so what it is said here is that the length, after designing whatever length value you get, so that actual theoretical length value, it is, increased by some factor of safety, you can say. So they are increasing it to be like 10 to 50% from the theoretical value, they are increasing to account for what, non idealities of the in the flow. Okay, so and for the settling of the particles also, they are increasing the length. So here they are taking in account to be 30%, they are increasing out of 15 meters, so they are 30% of 15 meter, they got it to be 20 meter. Okay, so they 10 to 15 per 50%, any value you can take, so they are taking it to be 30%. So 30% of 15 meter is, it is your 20 meter they are getting. Okay, so now everything you got, like length, width, and depth, everything you got. So the final answer, it comes out to be this one. Okay, it comes to be this one. Clear? So this is a design based yeah, this one numerical. So you need to go through one, two times, three times. So you need to go through, then you will understand it better. Okay. So today I will share it with you, this material, so that you can go through at your home. Okay. So next is your, after your Creed chambers is your, okay. So we are going through the aerated grid chambers. Okay, so aerated grid chambers, I already told that it is, like it is a grid chamber where your spiral flow aeration tanks are there, and it is usually it is designed to provide detention period of 3 minutes. So like here, see, you see this these things are mentioned here, no? So these things you need for your numerical purpose. So what is the detention period for a aerated grid chamber? So what are the air diffusers are located, at what location they are located? Okay, what is the grid hopper depth? Okay, so all these things you need to note it down for your numerical purpose. Otherwise your definitions, no one would be asking you about all these things. Okay, only the designing problems are important, and you should know the values. Okay, so here you see, like these things you go through. Okay, this all the values that are given, you see, like what is the velocity value, or what is the water depth value, what is the detention period time, so what is the length to width ratio. So all these things are written very nicely. Okay, it's all are mentioned here very nicely, you can go through, because I will be doing the numerical here, and if you don't understand some values what are they are mentioned here, so you can directly go to your this note. Okay, so when you go to this note, you will find out the values that are mentioned here. These are only used in your numericals. Okay, so like let me do this discuss this aerated grid chamber numerical. Okay, then you will automatically understand whatever values are given here. Okay, so let's see what it is given in the question is that design an aerated grid chamber for treating and municipal wastewater with average flow rate of 0.5 meter cube per second. Okay, within bracket they have given the MLD, that is your 43.2 MLD. Then assume the peak flow rate to be 3 times the average. Okay, so what? Let us see how to solve it. So your peak flow rate is given, okay? It is given as your peak flow rate, you see. Okay, someone has message, let me see. Ma'am, battery 10% more card. Okay, Wangthoma. Okay, Rangthoma, Dev Burma. Okay, no problem. Roll number 32, let me note it down. Okay, no problem. What can you do now? No current. Roll number 32. Okay, I have marked you present. Okay. Okay, welcome. Okay, so let's continue. So your peak flow rate is given to be 0.5 meter cube per second, okay, and it is given it to be like you have, it is a 3 times that of the average. And what is the average? It is your 0.5 meter cube per second. So you multiply it, okay, then you will get 1.5 meter cube per second. So now they are, since here your detention period is not mentioned, and just now we have gone through the edited this grid chamber notes. So there it is mentioned that the detention period or the detention time for the aerated grid chamber, it is to be 3 minutes. Okay, it is 3 minutes. So they have converted it to seconds, so it is 180 seconds. Okay, now they are finding the volume, aerator volume. So what is the aerator volume? You have to multiply the peak flow rate and the detention time. Okay, they are getting it to be 270 meter cube. So now, in order to drain the channel periodically for routine cleaning and maintenance, use two chambers. So for there are two chambers, okay, because if one chamber it is being cleaned, so one chamber it should be in operation, okay. So like two chambers are being used. So like you have to find the volume of one aerated channel. This is the volume for your two channels. This aerator volume, it is for your two channels, and now we need to find out the volume for each channel. So you need to divide it by 2. Okay, so they are getting it to be 135 meter cube. So now you need to find out again the dimensions, since you are designing the grid chamber. So you have to find the length, width and depth. Okay, so here to determine the dimensions of the channel, they assume the depth of the channel it to be 3 meter, okay, and the width depth ratio to be 2.2 is to 1. So all this value you will get it in the notes. Okay, this 3 meter, this width depth ratio, all these things you will get it in the notes. You please go through the note. So now they are finding the width of the channel. So how to find the width of the channel? It is depth multiplied by 2. Okay, so depth is 3, okay, and your it is multiplied by 2, so they are getting it to be 6 meter. Okay, so your width depth ratio, no, so that is why width by depth is equal to your 3 is written is equal to 3. So like they are multiplying it and they are getting it to be 6. Okay, so length of the channel, now they are finding it is 135. That is the volume of one aerated channel is divided by your area. Okay, this is 3 meter into your 6 meter, that is your depth into width. Okay, so they are getting it to be 7.5 meter. So again they are increasing the depth, increasing the length of the chamber, okay, by 20%. Here they are increasing. So they are increasing the 20% of 7.5, it is your 9 meter. So the provided length it will be 9 meter. Okay, so finally they are writing it to be, hence to use two chambers each of size 9 meter by 6 meter by 3 meter. Okay, 3 meter to you have assumed it, and 6 meter you have got it here. Okay, and the length you got it finally to be 9 meter. Okay, so now since it is a aerated chamber or aerated grid chamber, so it is there you have to supply air. Okay, air is there. So how much of air you will be supplying, in the question it is not mentioned. So in the notes you will find it out, you will found obviously. So it is 0.03 meter meter cube per minute. Okay, it is 0.3 meter cube per minute into per minute by meter. So into your 9, what is 9? 9 is the length. That means this much of length, for 9 meter length of the chamber you have to supply the air. Okay, 0.03 you have to supply air, so you have to multiply both, okay, with the length. So you are getting it to be 0.27 meter cube per minute. That is your air requirement answer. Okay, and now also you have to find out the volume, how much of grits are produced daily. Okay, how much of grits are produced daily in the chamber. So for that you have to assume that 50 meter cube or 50 meter cube per meter dot cubic meter of sewage of grit is produced by the incoming sewage. Okay, so there is one formula. You see this formula. Okay, this is the formula for how much of volume of grit is produced daily. So it is peak flow rate of sewage into grit produced per meter cube of sewage. So peak flow we have already found out it to be 1.5. Okay, and what is the grit produced? It is 24 into 3600. Okay, sorry, this one they have converted to seconds per day. Okay, this 1.5 they have converted, so 24 into 60 into 60, and this is 50. Just now we have assumed 50, so the 50 meter cube by 10 to the power 6, since it is million. Okay, since it is million, they are converting it to meter cube per day. Okay, so there are, you are getting the answer finally to be 6.48 meter cube per day. So this much of 6.48 meter cube of grits are produced per day. Okay, so this is about your aerated grit chamber numerical. Okay, little bit confusing, or you can say because you are doing it for the first time, so it will be a little bit confusing. But then also if you go through 3-4 times to the same numerical, then you will understand it slowly. Okay, okay, so it's 10:42. Okay, then I'm also tired by explaining. So let us end it here today, okay? Detritus tanks and skimming tanks I will be doing in the next class, okay? We will be doing it in the next class. So let me take your attendance. Friday I have continuously 3 class, so it's very tiring because first 2 is with you, then again third class with this section B, 3 class continuous. It's very tiring. Okay, roll number 1.
Yes, ma'am.
Okay, roll number 2. Roll number 2, 3.
Present, ma'am.
Okay, 4,
Present, ma'am.
7. Roll number 7, 8, 9,
Present, ma'am.
okay, 10, 11. Roll number 11 is there. 11, no. 12,
Present, ma'am.
okay, 12. Then 13,
Yes, ma'am.
okay, 14, 15, 16, 17, 18, 19, 20.
Present, ma'am.
Roll number 20, right?
Yes, ma'am. Present.
Okay, okay. 21,
Yes, ma'am.
okay, 22,
Yes, ma'am.
23,
Yes, ma'am.
24,
Yes, ma'am.
25,
Present, ma'am.
26,
Present, ma'am.
okay, 27, 28, 29,
Yes, ma'am.
Okay, 30,
Present, ma'am.
31, 33,
Yes, ma'am.
33, okay, 34,
Yes, ma'am.
35, 36, 37, 38, 39, 40,
Yes, ma'am.
okay, 41,
Present, ma'am.
42, 43,
Yes, ma'am.
okay, 44, 45,
Present, ma'am.
45 present, 46,
Present, ma'am.
okay, 47, 48, 49, 50. Okay, anyone is left out?
Present, ma'am.
Yes, I cannot hear you. Roll number 11.
Yes.
Okay, 11. Then roll number 18. Roll number 18. Okay. Who else? Anyone else? Roll number 22. Roll number 22. 22 I have given present. Anyone else? Roll number 2. Roll number 2 is there. Roll number 2. Then roll number 5, 6, 7, 8. Then roll number 10. Roll number 14, 15, 16, 17. Then roll number 19. Then 27, 28. Then 35, 36, 37,
28 present.
yes, roll number
Roll number 28 present.
20, 28, okay.
Yes, ma'am.
Okay, then 35, 36, 37, 38, 39, no one, okay. 42, no one, then 44, 47, 48, 49, 50. Anyone is present from here? Okay, no one, okay then. Okay, so meet you in the next class, okay, that is on Wednesday.